Hi, it's Mr. Miller. Welcome to another video. This one is on precision and accuracy. Let's go ahead and get started. So we're going to talk about accuracy first. And accuracy is how close our measurement or calculation is to the actual or accepted value. So we've done a lab where pi was the accepted value, and the accuracy is how close our answer got to pi. Okay, and to determine accuracy, you really need to have a lot of data points, a lot of samples, and probably better than just one sample per group would be to take all of the groups in my classes and come up with an average of the results, and that would give us a good, hopefully a good amount of accuracy. The accuracy is an indicator of systematic error. So if you have systematic error, something wrong with your experiment or one of your devices out of calibration, all of your measurements are going to be off of what the actual value would be. And now here's a diagram of accuracy. Both these diagrams represent good accuracy. If you take the average of all the values, they average out to be right at the origin of those crosshairs. So we would call this, so now we're going to look at the other side of things, and that's precision. And precision is a measure of how close repeated measurements are to each other. So if you use a ruler to measure a length of, for example, a block or the diameter of a CD, it's if you make several measurements, it's how close each of those measurements is to the others, and that would be precision. Okay, now precision is an indicator of random error. If you have, you're going to have measurements that are going to be surrounding the actual value, and as long as they're very close to the actual value, we would say that that is a precise measurement. Now this graphic demonstrates two sets of measurements that are precise. You see they're very tightly packed together. They're both showing measurements that have very little variation from each other. Now if we look at this graphic here, that's the graphics that we've seen plus one other. It shows good precision in the upper left-hand corner. It shows good precision, but not so good accuracy. So what we're saying is that we have precise measuring tools. There's very low random error, but we have systematic error, so meaning that all of our measurements together are being thrown off the actual value by the same amount. In the upper right-hand corner, that's just a mess. That's poor precision and poor accuracy. That means that we weren't using the right measuring tools, we didn't have a very good experimental design, we weren't careful. We don't want our data to look like that. That would be a bad experimental result. Lower left-hand corner, we have high precision and good accuracy. That's what we're striving for. We're striving for repeatable measurements and as many errors in the experiment eliminated. We can't eliminate all of them. We can't reduce our measurement uncertainty to zero, but we can do our best. We can use the right tools to measure and carefully measure those and eliminate those factors that we can. On the lower right-hand side, that's a series of data that not very precise, but the accuracy is good. That shows that our measuring tools were not as precise as they could have been. They didn't have as fine of measurement as we could. In other words, instead of using a ruler that was measured in divisions of meters, maybe we should have used the ruler that was divided into measures of millimeters. We would have had more repeatable results. Okay, so here's your multiple choice question. Which of these graphs, both the target graph and the line graph, represent a high amount of systematic error but very little random error? Go ahead and answer that on your summary form that goes along with this video, and feel free to pause or rewind as necessary. Welcome back. Now we're going to talk about measurement and how we use these ideas of precision and accuracy along with our measuring tools. So here's a graphic of a ruler, and this is divided into centimeters, and we're going to measure the length of that pen. And if you look at the blow up, the length of the pen is somewhere between 4.7 centimeters and 4.8 centimeters. We have to report that it's 4.7 centimeters, plus we need to estimate that last digit. The hundredths place is an estimate. The ruler is only marked to the tenths. We have to estimate to the hundredths. We can't estimate more than the hundredths, better than the hundredths. We couldn't throw a thousandths place in there. That would be overstating the precision of our device. And this determines our significant figures for our measurement. You can see that we have 3 significant figures in our measurement. That's because our measuring device is precise to that many digits. Now here's another example. You may have seen these in chemistry last year. This is a graduated cylinder, and you learn that you measure the volume at the bottom of the meniscus, or that little curve. And in this case, it looks like the liquid is at 32.0 milliliters. We have to estimate to the digit in between the divisions on the graduated cylinder. So that's why we have to put a 0.0. So all 3 of those digits are significant. Now let's say that meniscus was up just a little bit, then maybe we would have written our measurement down as 32.1 or 32.3 milliliters. Okay, we have to have that final digit in there, that estimate digit. Only one estimate digit, but we have to have that estimate digit. Okay, so now here's a free response question for you. So, for each of these items, please write down the measurement that you would record on your data sheet, and look forward to seeing you at our next video. Have a good day.